Hey Calculus class! Today we're going to talk about topic 61, the integral test and p-series. So I know I have repeated this before, but I want us to always keep the following goals in the back of our head when we are doing infinite series. So for the AP test, you are required to determine whether or not a series converges or diverges. You do not necessarily have to determine the value at which the series converges. And in order to do this, we must use multiple different tests to determine if a series converges or diverges. And there is a lot of gray area when doing this. So let's review the tests we have already talked about. The first one is the nth term test for divergence, which says that if you have the limit as n approaches infinity of a sub n does not exist, or if the limit as n goes to infinity of a sub n does not equal 0, then the series is considered divergent. And something to keep in mind, if the limit as n approaches infinity of a sub n does equal 0, this does not always mean convergence. It only tells you that you must perform another test. The other test we have is the geometric series. And if the series is in the form as the sum of n equals 1 to infinity of a times r to the n minus 1, then if the absolute value of r is less than 1, then the geometric series converges to a over 1 minus r, where a is your first term. Or if the absolute value of r is greater than or equal to 1, then the geometric series diverges. Our third test is the telescoping series. So if subsequent terms cancel out previous terms in the sum, then you have a telescoping series. And you may need to keep in mind that you may have to use partial fractions or properties of logs to put into appropriate form. And if the sum collapses into a finite number of terms, and the limit is a finite number, then the series converges to that number. If the limit does not exist or is infinite, then the series diverges. And just to keep in mind that only the geometric and telescoping series will converge to the number that you get. So let's look at a series as an area. Let a sub n be a positive decreasing sequence, and the integral from 1 to infinity of f of x dx, the area under the curve. So keep in mind, the sum of the series is the same as the sum of the areas of the rectangles. So our first case is if the sum of the areas of the rectangles is greater than the area under the curve, because the area of the rectangles is an overestimate. So just as like my picture shows, the area of the sum of the rectangles is bigger than the actual area under the curve. And if the area under the curve is infinite, then the series must have even bigger area, so it is infinite too. Case 2 is, in this case, the sum of the areas of the rectangles is smaller than the area under the curve, because the area of the rectangles is an underestimate. So if the area under the curve is finite, then the series must be a smaller value and it converges. The value of the integral is not the value that the series converges to. We do not need that value. We only want to know if it converges. So this leads us to the integral test. So if we have the sum of a sub n, and if it is positive decreasing series, and f is a continuous function on the interval from 1 to infinity such that f of n equals our sequence a sub n, then if the integral from 1 to infinity of f of x dx diverges, then we can say that the series diverges. If the integral converges, then the series converges. And if the terms are not positive, then negative area will cancel positive area. And if the terms are not decreasing, then some rectangles will lie below the curve and some will lie above. So therefore, the integral test will not work. So let's look at some examples. So we have this series 1 over n, and we should all recognize this as the harmonic series, which means we all should already know that this series does diverge. But we're going to use the integral test to prove it. So I always want to take the limit of 1 over n as n is approaching infinity, and I could just do that in my head for this one, and I will get 1 over infinity, which gives me 0. So that means that I'm not sure if it diverges. So if I wanted to use the integral test for this, I need to double check to make sure that my terms are positive and decreasing. So if I was to list out the first couple terms of 1 over n, you would get 1, then 1/2, then 1/3, 1/4, 1/5, etc. And as we keep going, you should notice that each term is positive, and as we increase the number of terms, the terms are getting smaller and smaller and smaller. So therefore, I can use the integral test. So I'm going to go ahead and set up my integral, and I'm going to look from 1 to infinity, since n equals 1 of 1 over x. Since this is an improper integral, I'm going to take the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. I'm going to integrate 1 over x, which is the natural log of x. And since I know that these terms are positive, I don't have to worry about the absolute value sign. Won't change anything. And I can go ahead and evaluate this integral from 1 to t. So when I do that, I get the natural log of t minus the natural log of 1. And the natural log of 1 is just 0. So I am just going to take the limit as t approaches infinity of the natural log of t. And as the natural log, the graph of natural log of t, as t is getting infinitely large, so is the natural log. So therefore, this integral diverges. So since the integral diverges, then we can also say the series diverges. And since we know that this is the harmonic series, it will always diverge along with any series that is a multiple of the harmonic series. All right, let's take a look at this series. So I want to double check and test for divergence first. So taking the limit as n approaches infinity of 1 over n squared, I'm just going to get 1 over infinity, which gives me 0. So therefore I need to do a different test. And if I wanted to use the integral test, I need to double check to make sure all of my terms are positive and decreasing. So if I was to list out my terms, I would get 1, 1/4, 1/9, etc. And each term is positive and that they're getting smaller. So therefore it is okay for me to use the integral test. So I'm going to set up my integral from 1 to infinity. And since it's an improper integral, I'm going to take the limit as t approaches infinity of that integral. I can rewrite 1 over x squared as x to the negative 2. And I can add 1 to the exponent, multiply by that new exponent. So my antiderivative is negative 1 over x. Evaluate at t and 1. Now I can go ahead and take the limit, and I will get 1. So therefore, since this integral converges, then this series also converges. And in order to get convergence, you not only need the terms to go to 0, but you also need them to go to 0 at a very fast rate. All right, so now let's try this one. All right, so for this series, I'm going to first check for divergence. So when I take the limit as n approaches infinity, and after doing some L'Hopital and reevaluating the limit, you would get 0. So therefore, I need to do a different test. So if I wanted to use the integral test, I need to first check, are the terms positive? So if I was to list out each term, yes, I would get that the terms are positive. And then I need to check to make sure if each term is decreasing. Now for this sequence, it's a little bit more work. So if it's not very noticeable that the sequence has decreasing terms, then you can always check to see if the first derivative is negative. Because we know that whenever the first derivative is negative, you have a function that's decreasing. So to double check, I'm going to take the first derivative of x over e to the x squared. And after using the quotient rule, I get e to the x squared minus 2x squared times e to the x squared all over e to the x squared squared. Simplified a little bit. Continue simplifying. And to double check to make sure that this will always be decreasing, well, I know I'm looking specifically when n is always greater than 1. So if I was to put in a value that is greater than 1, you will see that my derivative will always be negative. So therefore, each of these terms are decreasing. So that means I can go ahead and set up my integral, rewrite it as a limit as t approaches infinity. After rewriting it as a limit, you want to take the antiderivative to get negative 1 over 2e to the x squared. And to get that, you will want to use u substitution. Now I'm going to go ahead and evaluate from t and 1. And go ahead and take the limit as t approaches infinity. When I do that, I go ahead and get 1 over 2 to the e, which is a finite number. So therefore, since the integral converges, then the series also converges. Now the integral test leads us to what is called the p-series. So we're going to let p be greater than 0 and a fixed number, so that then we have the series of 1 over n to the p power. So that would look something like this. 1 over 1 to the p plus 1 over 2 to the p plus, and so on. So the first case is if we have the harmonic series, so basically when p equals 1, we know that this series diverges. And we know that this is the harmonic series, and basically the harmonic series is a p-series where p equals 1. And since the harmonic series always diverges, then when p equals 1, the series diverges. Our second case is if we have a p-series and p is greater than 1. Then, if I was to take the integral of that series and go ahead and rewrite it so it's a limit, and go ahead and take the antiderivative. After I take the antiderivative, I can go ahead and evaluate from 1 to t to get the following. And I can simplify this a little bit more. Since I know this is 1 to some power, this numerator will always be 1. And I can go ahead and factor out a negative in this exponent to get the following. And since I know that p is greater than 1, then the exponent on t will always be negative because of this multiple negative 1 out here. So therefore, I can move this negative exponent down to the bottom to get the following. Now when I go ahead and evaluate the limit as t approaches infinity, I'm going to get that this piece right here will be infinity because it's the only one with t. So therefore, making this fraction go to 0. So I am left with 1 over p minus 1. And since p is always greater than 1, I have a finite number. So therefore, this integral converges. So therefore, the series converges. Our third case is if we have the p-series 1 over into the p, but this time p is between 0 and 1. So if I was to use the integral test, again, set up the limit, evaluate it at t after I take the antiderivative, and this time, since p will be between 0 and 1, then the exponent on t will always be positive. So therefore, I'm going to keep this on top. So when I do that, then I'm going to get infinity over some number. So therefore, this fraction becomes infinity plus some finite number, which will just give me infinity. So therefore, this integral diverges. So the series will diverge when p is between 0 and 1. So in the general case of any p-series, you have if p is greater than 1, then the series will converge. If p is between 0 and 1, including 1, because then it will be a harmonic series, then the series diverges. So let's look at some examples where we identify the p-series. So if we are given this sequence, in order for us to figure out if it converges or diverges, I want to rewrite it as a series. So if we look at the pattern, if you notice, here's n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. So therefore, we should notice that we have a pattern, and we can rewrite this sequence as the series of 1 over n times the square root of n. And I can rewrite this so it has a single exponent, which would just be n to the 3/2, which does give me the form of a p-series, and the p-value is 3/2. Well, since p is greater than 1, this series will converge. Okay, let's look at this example. Since this series is a sum of two series, we can break it up and look at each one individually. So I'm looking at the first series, n to the negative 1.4, and then the second series, 3n to the negative 1.2. And since we have to keep in mind that if each individual series converges, then the original series converges. And so if I look at n to the negative 1.4, rewrite it so I no longer have a negative exponent, you will see that this is a p-series where p equals 1.4, and that's bigger than 1, so that series converges. And if we look at the other series, 3n to the negative 1.2, rewrite it without any negative exponents, you'll see that this is a multiple of a p-series where p is 1.2, which p is greater than 1, so this series converges. So therefore, since both individual series converges, that means the entire original series converges. Well, I hope you enjoyed learning about the integral test and p-series, and I will see you in class tomorrow. Have a good night.